The purpose of this recording is to go through test 2, practice test 2 solutions. So it's going to cover multiple choice plus some of the short answer, so about 2 pages of the exam. So let's start with the multiple choice. Here we're given that we have a capacitor of capacitance C, and we're told that, or asked, what happens if the area of the capacitor triples and the distance between the plate quadruples? What's the new capacitance? Well, if we look over here at our capacitance equation, we see that the capacitance is proportional to the area over the distance between the plates. So in this case, we're tripling the area and we're quadrupling the distance. So that's going to be the new capacitance that we get is 3/4 of C. So the answer is C. Question 2, 2 loops each carry current I in opposite directions. If the loops are held parallel to one another and then released, which of the following best describes their expected behavior? You may ignore any influence of gravity. So if we trace this current around, we see that we have a current going to the left here in the front. This is 3-dimensional, and then in the front you have it going the opposite. So if you remember that opposite currents repel, then you'll know already that the loops will repel each other. But if you don't remember that, then you can apply right-hand rule number 1 to get the magnetic field direction. So say I wanted to find what was the magnetic field down here on the bottom loop, then I would point my thumb in the direction of I for this loop, curl around, and find that the magnetic field due to the top wire is here, pointing out of the page. And then I would use right-hand rule number 2 to get the force direction. So to do that, I put my fingers in the direction of the current, and then I curl my fingers upwards to the magnetic field, and then find that the force is that way. If I were to do that to this loop, I'd also find a force outwards. So yes, the loops will repel one another. Question 3, a charged particle moving in the same direction as a magnetic field would experience, and we have different directions of forces. So here we have a charge that's moving in this direction, and we have a magnetic field also in that direction. So remember that the force is equal to QVB sine theta. In this case, theta goes to 0, so that means force is equal to the sine of 0, which is 0. So there's no force due to the magnetic field. Question 4, a clockwise current is induced in the loop by moving which of the following into the center of the loop? So we imagine that we're moving this from our perspective, and we're moving these things. So we have a magnetic north pole. This is option A. Magnetic north pole is moving into the page. So the flux is increasing because the field lines are closer and it gets more intense close to the magnet. So we're increasing the flux, and that increase is directed into the page. So since that flux is increasing into the page, Faraday's law says that we're going to have a current that counteracts that. So I turn my hand around, point my thumb upwards, and then I'll find that the current is going to be counterclockwise. So that is not the direction that we found. If we have a magnetic south pole that's now being moved into the page, then again I'm increasing the flux, but the direction of that flux is out of the page. So that increase is going to be counteracted. I'm going to point my thumb into the loop to counteract that change in flux. And so we'll find that the direction of I is going to be clockwise, which is the same. So B is a possibility. Now C is a magnetic north pole that now I'm pulling it out of the page. So it's pointing towards a loop but being pulled out. So in that case, the flux is decreasing, but the direction is into the page. So I want to reinforce that flux that's getting lower. So I keep my thumb pointing inward, and that tells me that the current will be clockwise. And so that's also a possibility, and the answer is D, both B and C. Question 5. What direction is the magnetic field due to a straight wire at point P? So this is right-hand rule number 1. I point my thumb in the direction of the current, and then I hold the wire, curl my fingers around, and I see that my fingers are going to point into the page at the point at where P is. So the answer is C. Question 6 asks to draw the magnetic field lines for this configuration of magnets. So remember that field lines always go from north to south, and they have these butterfly loop patterns that are characteristic. And remember to put the arrows are important because they tell us the direction of the magnetic field. So close in, we'll see this pattern, but as we get further away, there'll be interactions between the two. So I would expect a little bit of probably some squishing here on this side as compared to that side. And also, you would expect to see some interaction between these two poles. So the lines don't cross, but they can travel from there. Also, you'll see field lines going in. Question 7 is about a capacitance RC circuit. They're a fully charged capacitor that's connected in series with resistor. So this is a discharging RC circuit. So in this case, we want to first find the time constant tau, and tau is equal to RC, which is the 4,000 ohms times 1.50 times 10 to the minus 6 farads, which is equal to 6,000 times 10, or excuse me, 6,000, let's erase this. It's actually equal to 0.000 or 0.600 least seconds, which is equal to 6 milliseconds. The next question is, what's the voltage on the capacitor after one time constant? So we're asking, it's asking us, what is V after T is equal to tau? So if we look at our equation for the discharging RC circuit, we see that the voltage is V naught e to the minus t over RC. So going back to our equation, V is equal to V naught e to the minus t over essentially tau. So we're going to plug in for this. V is equal to V naught e to the minus tau over tau. Well, that's just equal to V naught e to the minus 1. So if we plug in our values, our initial voltage here is 6 volts. e to the minus 1, then that is going to be equal to about a third of the original. So it's about 2.2. Oops. Then the next question asks, how long does it take for the voltage to drop to half its initial value? So again, we're going to start with our equation, V equals V naught e to the minus t over tau, but now we're going to make t equal to half of V naught. So half V naught to the minus t over tau. And in this case, the V zeros cancel. And we're going to take the natural log of both sides so that we can solve for t, and then t is equal to minus tau ln of 1/2. So we already calculated tau, so tau is minus 6 milliseconds times ln of 1/2, and then calculate that value out, and then you'll find how long it takes for the voltage to drop to half of its initial value. Okay, now I think I'm going to take a break right there, and in the next video we'll start question 8.